Sure, absolutely. Perfect. Great. Please go ahead.
Perfect. Yeah. So thank you so much for introduction, Imogen, and good afternoon, everyone. It's really a great pleasure to be here. So the purpose of this talk is to give you a snapshot about our activity in the past couple of years centered around a concept that we call it a neuro-vector-symbolic architecture. And in this talk, I'm particularly showing you how it can help us to get computationally efficient machine learning and reasoning applications out of this concept, and especially what is the role of in-memory computing in some parts of this architecture. So who cannot be impressed nowadays by the advancements in AI, being purely in the perceptions like self-driving cars of the Tesla, which is deployed in real-world environments, or recently developed conversational agents like ChatGPT and DeepSeek. Although impressive, they are struggling with out-of-distribution generalizations. So they are facing, once they are facing with something a little bit out of its training distribution, such as this horse-drawn carriage, they have difficulties. You know, this Tesla car recognizes it as a first truck, then SUV, then again trucks come back. I cannot figure out which way the truck is facing, a person behind the SUV, a person perhaps pushing the truck, you know, the list goes on. And this happened, in fact, in summer in Fritikon in south of the winter tour in Zürich. And then if you consider perhaps the roads in Switzerland are kind of still in distribution compared to where Tesla has been training. But, you know, out of distribution event has unfortunately a very long tail. And I'm sure these systems have been improved, but essentially the same limitations still exist, and it applies also across other architectures and the modalities as well. So now let's jump into text and LLMs. I'm particularly considering here a GSM 8K, so it's a data set that is generated for grade school math. So these are very simple natural language questions that are designed for primary level school students to just read a natural language kind of question and do very simple for main operations in the arithmetic, you know, multiplications, additions, subtractions, division, with very few steps. I guess it was introduced in around 2021, and you know, now GPT-4 has the state-of-the-art results, perhaps by seeing enough examples out of these data set. Then recently, Apple did a very nice ablation, and they came up with a slightly different versions of the test questions. So they call it GSM symbolic, in the sense that the test questions were slightly out of the distribution. For example, you change the name of the person, but perhaps it has nothing to do with the outcome, or you change a bit of the distributions of the number, and then you see that the performance drops significantly. Then O1 preview came to rescue, and looks like the problem is solved. But you have a slightly different version of the data set, which is called GSM symbolic no ops. And no ops means that it's very obvious for us that inserting just no operation in the question. So, you know, having kind of distractors. For example, if Alice is collecting, I don't know, some avocados during some days of the day, perhaps the size of the avocados has nothing to do with the number of the avocados that Alice is going to collect, right? So these are no operation. They have nothing to do with the outcome, but these distractors will significantly degrade the performance of even O1 preview. Then at the beginning of this year, we had a very, very difficult data set that was generated by a mathematician. It's called Frontier Math. And then if you apply O1, this was kind of expected that it is out of distribution, and the O1 preview goes to below, let's say, 2%. Then, as usual, O3 came to rescue, and above 25% kind of accuracy in this extremely challenging data set that may take even a couple of hours for the expert to solve. But then a couple of weeks, just this announcement came out that Epoch AI, who is in charge of building and developing this data set was actually funded by the OpenAI itself. So the fact that OpenAI has data access to much, but not all of this data set is already actually a leakage. So once, so this is another indicator that once the data set is available and these models can do an extremely good job, but the moment that you will start to change the distributions, all of them, doesn't matter that which league they are coming from, they are going to have issues. What about the scaling solution? So not a problem. We have these out of distribution generalizations. Let's make the models bigger and bigger such that everything is eventually in distribution, right? So this is our particular recent analysis that we have done, that we essentially looked at the sample efficiencies of transformers in the lens of compositional generalizations. And what is the compositional generalizations? It's basically that let's imagine that we learn as a set of very basic tasks or very basic primitives. And then we are aiming to just combine the existing primitives or existing knowledge to do a slightly more complex task. This is, at the core of the human intelligence, where we learn some very basic things and then combine them to do more complex. So how sample efficient it is if we consider in distribution. So we imagine that the whole data set and everything is available within the distribution. So this is an example of multiplication, where normally the algorithm that human use is kind of a step-by-step multiplication, where we have just maybe two simple primitives. The first primitive is digit multiplication, right? So we multiply an integer by a digit, and then we reuse the same primitive, but perhaps we just shift to the right, and then eventually we add them together. So two main subtasks or primitives are sufficient to do this kind of universal multiplication. And here is the number of samples that the transformer models require to reach perfect accuracy by learning these two subtasks. Less than 200,000 samples is sufficient to get the perfect convergence on these two subtasks. And then once we provide these subtasks to the transformer and ask it to do the multiplications, it requires at least orders of the magnitude, in the orders of the millions example, to be able to just learn very simple multiplications. While we are expecting to, just with very few samples, to be able to kind of rewire these two basic subtasks to be able to get to the compositional generalization. But this is not the case. We need to, looks like what under the hood the transformer is doing is learning multiplications differently from the scratch, which has nothing to do by, let's say, combining the already existing knowledge. So the second lesson is that even if we can afford to make everything in distributions, they are not sample efficient by any means once we want to get and combine them to create more complex scenarios. So what do we do? Actually, Edward Lee, in the keynote of last date, clearly mentioned that pick just one of them. If you want to go with the reliable or very certain AI versus the intelligence, these two are very contradictory goals. But at the same time, there are some lessons that we can learn from particularly cyber-physical systems. And he was pointing them very clearly that instead of perhaps treating the AI in the control, just let's treat the AI at the sensor side. And then there are very well-established methods in the control, in the signal processing, that by design, we expect the data to be noisy. The second is to have the envelope protection, as we have kind of the analogy to the flight envelope protections. As we limit the actions that a pilot or an expert human can take, we can also limit the actions that AI can take by providing envelope protections as part of the compute part. Or relying on the formal methods, model checking, theorem prover, etc. But the only issue with this class of the techniques is that they are not normally scalable. So these are three interesting solutions to go about bringing degrees of the reliability inside artificial intelligence. And if we look at it interestingly, the common denominator across all these three different techniques is that there is an interplay between the neural computing and symbolic computing. And this is the Neuro-Symbolic AI community. And here I just listed 6 different categories of six different established categories of the neuro-symbolic computings for which these 2 components can create hybrid systems. Particularly, I'm interested about the 5th and the 6th categories. Neuro-symbolic in the 5th category is essentially like the neuro part. You could think of it like an LLM that is calling, let's say, a symbolic procedure, like an external calculator, by means of some API. So you have your LLM, and then there is some API call to your external tools, right? And this external tool can perform some of those computations fully externally. And in the 6th category, where the symbolic is in the bracket, is kind of you are bringing some of those symbolic computations inside the neural networks and then make it truly fully integrated systems. And this is where we call it Neuro-vector-symbolic architecture, or NVSA in short. And then the vector in capital means that it's kind of common language between the neuro and symbolic part, such that by using these vectors, we can kind of create a bridge by having symbolic computations inside the neural network. So the NVSA concept essentially complements deep neural networks with the machinery of vector symbolic architecture in a unified framework. And its component was mainly inspired by Daniel Kahneman, the winner of the Nobel Prize in Economics, Thinking Fast and Slow, where he was advocating for having essentially 2 main components and the systems. So system 1, which is all about the fast thinking, which is about the perception, and system 2 is about slow thinking and its reasoning. So for the NVSA, let me just walk through it from an example. And this example is just a simple example of the visual analogy. So if you have, a square and a triangle, and they are just changing the color, perhaps we are expecting that the color of this hexagon is also going to change or become like a pink. So it's a very simple analogy. So in the perception, we have mainly a neural network that looks at this scene or that's at this image, and then tries to kind of disentangle these kind of concepts or attributes that are necessary for doing some high-level slow reasoning. And in the reasoning, we are essentially relying on the vector symbolic architecture, or VSA, which is nothing but algebraic structure with very high dimensional vectors and a well-defined set of mathematical operations such as binding, unbinding, superpositions, etc., to emulate virtually any symbolic computing. In fact, this is Turing complete, especially if we add it with some memory mechanisms such as associative memory, so it can emulate any symbolic algorithm that we are interested. But with high dimensional representations and high dimensional vectors. So this is what has shown as these holographic representations between the 2. So this can be seen as a kind of symbolic tool, but it is not external. It's very much integrated inside the neural network. And then we can do, for example, the reasoning task here to find the answer about this analogy. In terms of the goal, our goal in system 1 or perception is about promoting compositionally structured representation. I will define it in a second. What does it mean? And we will see some example. Essentially, this means creating some disentangled representations about visual perception. But generating these representations is mainly in the service of the reasoning, means that this is necessary conditions to fulfill some of the reasoning tasks. And the goal in the reasoning part is to enable reliable yet scalable reasoning via distributed representation. As Edward Lee mentioned, in the 3rd category, we have lots of formal methods, but normally these methods are not scalable. So the game boils down to the fact that how we can actually make them truly scalable by means of right machinery that can tap into the resources of hardware software stacks of the essentially neural networks with very distributed representation. All right, so NVSA, what is particularly maybe interesting is that its hardware and software realization is informed and benefited from in-memory computing. Perhaps I don't need to motivate the concept of in-memory computing for this crowd here. But basically, in hardware realizations of NVSA concept, we try to utilize some of these properties of the in-memory computing. I mean, besides all the kind of the advantages that we could get by having stationary memory and then saving, von Neumann bottleneck, there are also some other properties that they are quite interesting, doing these vector matrix multiplications, of course, in constant time, crystallization, which is especially mostly these kind of memories that we are using at IBMs are based on the PCM. So these are very, they have a rich dynamic range. So you could think of them as a proper analog storage, perhaps for continual few-shot learning, or a stochasticity, and the kind of noise that is available in device. I will show it clearly how this stochasticity could become a useful computational primitives in some of the system one's kind of perspective in the NVSA. And in NVSA itself, in the software side, we started from kind of robust and very efficient inference. So in 2020, we showed that we can make at a scale a very highly robust vector symbolic architecture inference on top of in-memory computing substrate. Recently, we showed that projections of kernel tricks can be done very efficiently by using in-memory computing. And in fact, it can approximate any nonlinear functions by using the kernel trick. And then if the area or essentially the parameter as is an issue, we can just stack these tiers of in-memory computings on top of each other, supporting or going towards kind of mixture of experts by having these 3D mechanisms such that each expert can be activated at a constant time. So essentially enlarging the system one kind of component of the NVSA. So this line is pretty much on towards making robust and efficient inference of the system one. And then we also looked at the learning part, how this machinery could help to kind of rapidly learn, perhaps from few examples. These were mainly applied into the biosignal processing, like the EMG classifications that is shown here, that with very few examples, you can perform kind of in-sensor learning, because also the cost of the learning is relatively simple by doing kind of prototype updates. There is no need of the gradient propagations, etc. And then at the interface of, let's say, system one and system two, we work on disentangling representations, how we can use some of the properties of the in-memory computing to help to get a better disentangled representations for NVSA, and lately towards making really a scalable and scalable solutions for the abstract reasoning. So in the rest of my talk, I will focus on first in disentangling representations, which is a kind of hardware software code design that exploiting in-memory computing for providing disentangled representations in service of system two. And in the system two for abstract reasoning, I will just mainly focus on the software part. There is no in-memory computing related to that yet. All right, so in visual abstract reasoning, we focus on the benchmark of Raven progressive matrices. This is the de facto standard for the human IQ test. As it is shown here, it's simply a 3x3 matrix where we have several objects, and the objects can have different shapes, colors, sizes, different set of properties. And there is a fixed number of the rules that is governing the relations of these attributes. For example, maybe the color is constant across each rows, or maybe the number of the object is adding from first row to second row to the third row. So for having a perspective on the NVSA, we first start on just focusing on the perception side, because what we need to get is not just only a classifications problem, but also kind of disentangling these attributes of the interest. And these attributes are very critical to be able to support the rest of the reasoning tasks. So we had a trainable neural network, and what is we call just simply a disentangler that I will open it up in a second. And it has just a code books. It has just access to set of code books of the concepts. And then what does it look So for example, let's say that we are interested in the number of the objects, right? So for each of these panel, we just want to extract the number of the object as a property. So there is 2 objects, 1 object, 3 object, 1, 1, 2, 1, 1, 3, and then the question mark. So this is one attribute that we, or one concept that we want to disentangle. You know, there are some other concepts, you know, like the shape that perhaps is changing, or the color that is constant. And then once these disentangled representations are provided, then we can feed it back or kind of transform it to some other space of the interest, and then apply a set of rules to perform the reasoning, and then eventually generate what is the missing panel. Let me first focus on the perception part. So for efficiently disentangling this representation, what we have is kind of a dynamical system. So let's say that we have a purple hexagon that is sitting in this part of the panel, and the attributes that we are interested in, its position, its shape, and its color. So one way is to just pass it through a few layers of the convolutional neural networks, and then get a high dimensional representations, or kind of distributed representation that is entangled. Entangled in the sense that all these properties of the interest are kind of superposed or bound together. And then we have a dynamical system that is called a resonator network that uses the VSA algebra to be able to search in this space in superposition. Because one way to just look at this in brute force is that, let's say that if you have 100 attributes in the color, shape, and the position, so the combinatorial expansions of them is like 1 million kind of combinations. So we are searching in 1 million combinations. But instead of just searching on those 1 million combinations, we are trying to just have very compact code books. So this X transpose, Y transpose, Z transpose, they are very small code books that they are defining the cardinalities of each attributes, like here. So for example, we have 4 different shapes, 4 different positions, 5 shapes, and then maybe 10 colors. And in each iteration, this is a dynamical system. So this S vector that is generated by neural network is a superpose, or kind of an entangled vector. In each, let's say, factors, we are trying to kind of unbind. So this is, you could think of it, let's say that the S is a multiplicative factor of all these generative factors. So we can kind of unbind them with an estimate of shape and color. So to be able to get an estimate of the positions, we unbind the we get rid of the effects of the shape and the color. Or to get the positions for the shape, we get rid of the effect of positions and the colors, and so on. You know, for the color, we kind of unbind the effect of the positions and shape to be able to get a better estimate. And then once we got this estimate, we update or kind of beliefs. And this is the concept of the search in superposition. So instead of just go to the combinatorial expansions of all these possibilities, you have a set of compact code books, and you just search through them. And then after a couple of iterations, hopefully we find the correct disentanglements. And these attributes could be used later for the next stage of the system. Let's go through its implementation. So you have the simple neural networks. You can for sure, of course, implement it in the in-memory computing, not a problem, because normally these weights are stationary. But I'm just opening up this disentangler part. So we have an entangled vector in the input, and yeah, and then the phases that I showed is essentially for that dynamical system. We need to first do a search on the code books. So we store these code books in a, let's say, 1 core in the in-memory computing, here is in PCM. Then we get some similarity, kind of executing a similarity search that shows us the similarity for each of these code books. Then we do a projection, which is essentially nothing but the transpose of these code books or transpose of this crossbar to get a weighted superpositions of these vectors again to get the projections. And then we kind of feed back these projections again for the next iteration. So this is for one of the factors, let's say for the shapes. And then we could have kind of parallel architectures for different factors to do them in fully parallel, or we may want to time multiplex them across different factors of the interest. What was interesting is that if you just naively implement a system and simulate it on perhaps on a digital way, you will see that it faces limit cycles. Limit cycle in the sense that, let's say this is the estimate for the color at time t. In 4 cycles, you go back to the same estimate, and then you kind of are stuck in these limit cycles. The more iterations that you do, you cannot just get out of these limit cycle breaks. But you know that most of these MVM matrix vector multiplications operations that we are doing is very noisy. So if you look at these similarity vectors, the reference one that you have in digital and the actual one that you measure out of the stochasticity of these devices, it's not a perfect fit. It's just a noisy cloud. And these stochasticity will help us that in each iterations, we are actually getting a different realizations of the similarity vector. So instead of getting to exactly this point, we are getting somewhere nearby, and eventually we can break the limit cycle. So kind of in this way, this stochasticity is a nice tool to remove these limit cycles and solve some of the problems that cannot be solved otherwise. So that was a hardware technique to bring from the in-memory, but we also observed the limited capacity in the sense of what is the maximum problem, and in terms of the size of the problem that can be solved by a given dimensionality. And here is again, for example, let's say the estimating the color, for example, for a given query vector. And we get linear projections to kind of different code books. Let's say we have blue, green, and the red. So for each of which we get a certain distributions. And then all we do here is to kind of linearly recombine these kind of estimates to get the projections. And then what we have noticed is to bringing a kind of local operator in terms of an activation can boost significantly this capacity, and we can have just basically maybe a simple sparse activations based on the values of the ADCs, and then once those values are surpassing a certain threshold, we can just activate that through, otherwise it will remain inactivated. And this helps a lot in boosting the capacity. So I here just put them together, these two features. So the first feature will help us to get a stochastic in-memory factorizer because it's noisy. And then the second one is to give us sparse activations. And then if we put them together, we kind of actually get at least 5 orders of the magnitude larger problem that cannot be solved otherwise. So here is the search space. So F is the number of the factors that we have. So for example, 2 factors here, let's say color and shape. And here is the size of the space. So for example, 10 into the power of 6 means that we have 100 code books or 100 elements in each code book. So we have means we have thousands. So if you have 1,000 elements in each code book, we have 2 factors, so it's 1,000,000 combinations. And for 1,000,000 combination, this dashed line is showing the brute force limits. Brute force limits, that means how many operations we need to do in a brute force fashion to just factorize or kind of disentangle this representation. So maybe 500, roughly 500 iteration is sufficient to just kind of factorize this problem size. And then we normally don't want to get to that brute force limit, right? Because some of these large problem sizes become impractical. So you see that quickly the baseline is the one that doesn't have a stochasticity. So it means it's running perhaps on a digital, or it doesn't have the right nonlinearity. Quickly reaches these limits. I mean, it can solve maybe very small problems with 100 code books. not a problem. It's even faster, 10 times faster than the brute force. But the moment that we expand the size of the problem means that you are having a more complex scene with a fixed dimensionality. By the way, this is the dimensionality of the input vectors, or let's say the output dimensionality of the CNN. You quickly hit these limits. And then in-memory factorizer can just go 10 times at least better, and there is no limit so far that we observe. And the same thing holds for more complex number of factors. If you have 3, if you have 4, of course, we have to go to a bit higher dimensions, but still we can keep the same benefits. So that was a kind of functional benefit that doing this stochasticity can bring, but of course there is the normal advantages in terms of lowering the energy because everything sits stationary, and then we can kind of take advantage of those other aspects. All right, so then we see that what is a prototypical system that can provide us this kind of disentangled representations, and now once we provide these disentangled representations, we send them to the reasoning part. And in reasoning part, just to give you a high-level idea, is to find the actual functions that can fit perhaps on this puzzle. So for example, what is the functions that if I had 2 and 1 gives us 3, or 1 and 1 is 2? And then you have a set of these functions that you define, you perform a search over them, and then generate a function that can actually match with this template. And this is a kind of a slow process in terms of the search. But of course, it's a very simplified picture. Normally, we don't have these discrete inputs. These are normally a probability mass function. So, searching in the PMFs is much more complex than just getting a disentangled representations, but this is just to give you an idea. So I will not go over the reasoning part at how it has been done, but you got just basically the idea. So let us just compare this reasoning performance with other alternatives that nowadays are available. So here I'm just plotting the reasoning accuracy, meaning that imagine that the disentangle part or perception part that I've shown you is perfect. It's an oracle. It can just gives us 100% accuracy in disentangling all the possible combinations of the attributes. So if we feed it to a state-of-the-art neuro-symbolic solver, it gives us 94%. And then we have started to look, what is the reason? The reason is actually time compute, because they have to do lots of heuristics, because the search of the space is very big. Imagine that what kind of functions you have to search. You have pretty much search for arbitrary functions with the PMFs, which is very hard. And then if we a bit relax those constraints, and we come up with this brute force one, which can for sure improve the reasoning accuracy to 97.5. But you need roughly 11 days to solve just only 2,000 instances of those puzzles. So it's really practically intractable. In NVSA, what we can do is to maintain more or less the same accuracy while reducing substantially the reasoning time, by 2 orders of the magnitude. Still, it is on the CPU, so you will see the demo. But there is also still, of course, many rooms to perform those kind of distributed operations still within the memory. And also, this was in 2023. We also recently benchmarked it with the GPT-01. It's just reasoning accuracy is not that competitive. And what is more important is that the compute time is actually getting on par with the brute force. Having said that, this is just only the time dimension. It is not the space dimension. We don't know where GPT-01 is running, perhaps at least a couple of A100, while here we just have a single CPUs that can pretty much run these kind of distributed representations in a real time. So you see here, these are different puzzles, and the perception is done in real time as well as the reasoning part. All right. So far, I've shown you this pipeline by going from, let's say, system 1 in the disentangling neural representations to kind of reasoning part. But this reasoning part, if you notice, is kind of knowledge-based in the sense that I have to know what are my rules. And once I have those rules, I can detect them and execute them. In other way, I have to hard code them. So for example, for solving these kind of Raven progressive matrices, maybe we have 4 different types of the rules. and those can be hard-coded with the, let's say, in the VSA algebra like this, and you provide that kind of the knowledge inside the system. And by the way, this is a very common properties of many neurosymbolic systems, and that's the reason that they become much more reliable in terms of handling out of distributions, etc. But the question is that, yeah, sure, you can provide it, but you cannot adapt it. If the puzzle is changing from one domain to other domain, what you're supposed to do, you cannot just have always expert knowledge. And this is the directions that in the last year we started to go, so towards learning to reason. And essentially, the gist of it is the following. We still do the same transformation. So you get the disentangled representations, you map them to these distributed representations of the VSA, but you try to kind of have a very generic, let's say, rule template. I don't want to go over the details of it, but it is all it is saying is that you have a sequence of, let's say, binding and unbinding operations, and all you have is a bunch of these orange kind of coefficients as your learnable parameters. Very economical way of putting your very few degrees of the freedoms on top of a rule template, a fixed rule template, and then maybe treat it as a, for example, a differentiable assignment problem in our case. And then try to learn these kind of the rules by the examples that are provided. And if we measure it, actually, this can also remain very robust against out of distributions test. Pretty much a very perfect accuracy with a very little variations if we change the seed, which is already 10 times better than the GPT, just running with these examples still with a perfect perception part. So hopefully so far I've shown you the two components of visual abstract reasoning, you know, the perception part, how it can be utilizing some of the features of the in-memory computing to get it much faster and much more efficient. And then in the reasoning side, hopefully some of those distributed representations that can speed up independently the kind of the computations that we are doing under the hood. But the third kind of dimension is still the generalizations, out of distribution generalizations. What is going to happen? Do we have a benefits here compared to the neural networks or not? So normally nowadays for testing them with the state-of-the-art neural network is to just generate again kind of a disentangled representations out of the puzzle. So imagine that the perception is perfect. So, or maybe we have access to this generative code of this puzzle, and all we provide, for example, is exactly a textual representations of that. For example, in row 1, there is 2, 1, 3. So this is the number of the object, 1, 1, 2, 1, 3, and then just ask the LLM what is the missing part. And this is a very ideal scenario. By the way, I mean, there are lots of efforts in the literature that they try to feed the actual visual part into kind of multimodal LLM, but they are all reporting very, very lower accuracy. So it means that still doing a good perception is still pending. But let's for the sake of this analysis, consider that the perception is perfect. So this is the kind of normal test that is available in the internet, and then perhaps also different versions of the GPT was already training on. So we made just a bit of extrapolations of this and then created larger matrices and inputs. So let's say what we call it iRaven-X as the extended 3 by 10, and then we could have also larger numbers of the manipulations, right? So for example, we can have 3 digits or 4 digits. And this is a rule of, let's say, arithmetic minus. So this number 611 minus 2 minus 551 perhaps gives us 58 if you pick the correct rule. And then we tested this on different LLMs. So this input range, so this is 3 by 10 node puzzle, and this is the input range going from 2 digits to 3 digits to 4 digits. GPT-4 goes just less than 10%. And this is with the self-consistency. And the self-consistency means that we allow them to run multiple outputs, maybe 7 or 10 outputs, and then we take the majority. So this is normally a technique that helps LLM a lot to do very well in this kind of reasoning tasks. If we take the Llama 3 7B, it's for very large arithmetic, it goes beyond 2%. Why NVSA learning to reason can maintain pretty much its performance if the dimensionality is properly set for this dynamic range of the inputs. And we also recently did with the O1. It's not doing much great. I mean, there is some, all of a sudden it is good with the 2 digits compared to 3 digits compared to the 2 digit, but yeah, it goes down for the 3 digits. So hopefully I can convince you that there is a role of the neuro-symbolic computing with a specific flavor of using distributed representations and the operators that they are scalable for machine intelligence. And I showed you how it can enhance energy and compute efficiency in the perception, especially by doing this kind of hardware-software co-design and exploiting in-memory computing physics. How it can be used for a fast and scalable reasoning, and then providing better OOD generalizations. Thank you so much for your attention, and I would be happy to take any question.
All right, thank you very much, Abbas. Let me stop the recording.